In this unit, learning target 10C hyperbolas. So a hyperbola consists of two smooth branches opening in opposite directions. So on our picture down here on our graph, we have one smooth branch opening up to the left side here and one smooth branch opening up to the right side. Together, both of those create our hyperbola on our graph. The turning point of each of those branches is called the vertex. So here I have the vertex as the blue dots right there. The hyperbola also has two asymptotes, and those asymptotes determine how wide or how narrow each part of our hyperbola will be, but they are always going to be symmetrical. So on our example here of our picture, I've got an asymptote with a positive slope and an asymptote with the same slope, but it is opposite, so it is negative. And as those asymptotes change, our hyperbola is going to either widen out like it is in this example, or if the slope is not as steep, we could have a narrow hyperbola. And we'll talk about how we can figure that out through different examples. Our final pieces of vocab have to talk about what we call this axis. So the segment connecting the two vertices is called the transverse axis, which is also the axis of symmetry. This is similar to our major axis that we had with an ellipse. The two foci also lie on our transverse axis, or our axis of symmetry. So here in the red dots, I have a foci on the left, and I also have a focus on the right as well. The center of a hyperbola is the midpoint between the two vertices. So for us, our center here is at 0, 0, and for the purpose of the rest of this unit, we're going to keep our center at 0, 0. The green points on here I'll talk about as we get down to the definitions, but they help us determine what our asymptotes will be. Just like we had with ellipse, there are two types of hyperbolas. There's the horizontal hyperbola, which is similar to the picture we have shown. So this is an example of a horizontal hyperbola. We also have a vertical hyperbola where they would be opening up, and I would also have a piece opening down. Now the type of hyperbola is based off of which variable is positive in the equation. So unlike in an ellipse, we're not going to have an x squared term plus a y squared term. Instead, we're going to either have an x squared piece minus a y squared piece, which in that case we'd get a horizontal hyperbola because the x term is positive. Or if we have y squared minus x squared terms, then we would have a vertical hyperbola because the y term in that case would be positive. And we're going to look at those two examples side by side next as we go down. So, looking at both of these graphs, on the left side over here, we have our horizontal example, and on the right side, we have our vertical one. Let's start with the equation for our horizontal hyperbola. So our equation here is similar to the ellipse, so I'm going to have an x squared over this a squared term piece, but now I'm going to subtract off the y squared over this b squared term, and it is still going to be equal to 1. A and B here do not have to be, one does not have to be larger than the other, so A could be bigger than B could be bigger than A, they could be equal, it actually does not matter. But what I do know is that my transverse axis in this case is going to be horizontal, since it is a horizontal hyperbola. My vertices do have to deal with the term that is positive. So because they're dealing with this x squared piece, they are my a values, and they're going to be x-intercepts. So they're at plus or minus a, comma 0, and up here, they are these blue points on those graphs right there. So I have a, comma 0 on the right, and then over here I have negative a, comma 0 on the left. These box points, they don't actually have a formal name. I've had old classes that like to call them box points because you're going to see they help us create a box in a little bit. But there are these green points up here that we haven't really talked about. They don't have a formal name. I've used to call them no-name points. I've had classes call them box points. You can kind of pick your favorite name for them. But they have to deal with this y term, and they're actually coming from the b. So in this case, I'm up here at 0, comma b because I'm a y-intercept. Or down here we would be at negative b, comma 0. So our quote-unquote box points here are going to be at 0 plus or minus b. Our foci are on the same axis as our vertices, so they are x-intercepts in this case, and they are at plus or minus c, comma 0. Now when we dealt with ellipses, we did look at a, b, and c and how they related. There's a different equation that relates them since we are dealing with hyperbolas now and not ellipses. So for a hyperbola, how we relate a, b, and c is actually going to be the Pythagorean theorem. It's c squared equals a squared plus b squared. Now I know that this gets really confusing to keep track of, but one way I think about it is that they're always opposites. So in an ellipse, I was adding in the equation, so I was subtracting down here in my c relating equation, but for a hyperbola, they're opposites. So if I'm subtracting in the hyperbola equation, then down here for the c squared equation, I'm going to add. Now the asymptotes, I told you, were coming from these b values. They're also coming from my vertices. So here, if I look at the slope of this line, it actually went up b and then went to the right a, and it's giving me that value right there. Now if I do the same thing and go down and to the left, I get another point on this curve. So this line right here actually has a slope of b over a. So the equation for this line will be y equals b over a times x. Likewise here, when I have this negative slope, I went up b and to the left a, so the equation for this line is actually y equals negative b over a times x. For both of them, the y-intercept is at 0, so if I'm in y equals mx plus b, then I have my slope here plus my y-intercept of 0. So down here, our equations for our asymptotes then are y equals plus or minus b over a times x. And the reason I called them box points is I can actually create like this invisible box going through them that runs all the way down to where they intersect the asymptotes along through the x-axis as I keep going all the way up, and I get this box shape. This is actually how I can help create and kind of draw the shape of the hyperbola. So using the corners of this box is what's giving me my asymptotes, and the slope there, since they're going up b and to the right a and down and to the left, or vice versa, and that's creating these two asymptotes as they go through. Then from there, the branches are starting at the vertex and they're curving out and they're getting close to the asymptotes, just like they would if I had a log or an exponential function or a rational function. We get really close to the asymptotes. They do that on either side, and then they also do it on the other branch as well. Now the reason I've had classes call them box points is because you kind of create this box using both the vertices and then these no-name points that we have. Okay, the vertical hyperbola is going to be really similar. The biggest difference here is that my y squared term is now positive, so I'm actually going to start with my y squared term. Now, a and b don't have to be larger than one another. One of them can be larger than the other, it doesn't matter, but I always keep the a term with the positive variable. So on our horizontal case, since x was positive, I keep the a squared term with it, but now since y squared is going to be positive, I'm keeping the a term with that, and the b term stays with our negative variable. The transverse axis this time is going to be vertical, since it's a vertical hyperbola, and the vertices now, instead of being x-intercepts, are actually up here and they're y-intercepts, so they're going to be at 0, comma plus or minus a. So if I label them on the graph, I have 0, comma a, and then 0, comma negative a. My box points are these green points again, and they're at x-intercepts, so they're at b, comma 0, and negative b, comma 0. And then the foci are again my red points up here, so they are y-intercepts, since this is a vertical hyperbola, so they are at 0, comma plus or minus c. Now the asymptotes here are not going to be b over a again, because my b value is actually my x value. So when I'm rising here to get the slope of this line, I'm actually going up a units, and then I'm going to the right b units, and I'm starting to create this kind of invisible box that we were looking at before as it goes all the way through these guys. Again, I have a positive slope for the equation on the right, so this would be y equals a over b times x, since we went up a and to the right b, and our negative asymptote will be y equals negative a over b times x, since it's going down and to the right. So both of these I can combine together and say they're at y equals plus or minus a over b times x. And if we think back to the equation, it should make sense that these two guys flip-flop here. Because when I talk about slope, we're talking about rise over run, and so I'm looking at the y value over the x value. So it's changing a distance of b, which came from our y variable, and then over a distance of a, which came from our x variable. On the flip side, when I flip-flop the positive and the negative values, the a and the b stay in the same spot. So now when I'm rising by a units and going over by b units. So that's why this guy is a over b if it's a vertical hyperbola from there. We're going to take this information and help us do a couple examples with it. So our first example we're looking at here wants us to, given the equation, find the vertices, the foci, and the equation for the asymptotes for each hyperbola, and then graph the hyperbola below. So let's start with the type of hyperbola. What I'm paying attention to here is that the x squared term is coming first, but more importantly, it's the positive number there. So what I really need to pay attention to is the fact that on this term, I have this x squared over 25 as the positive value versus the y squared over 16 as negative. That tells me that this is going to be a horizontal hyperbola that we end up with. The vertices then are going to be x-intercepts, so I'm going to get some number, comma 0, and we'll come back and find that. Likewise, the foci are also going to be x-intercepts since those are both on that axis of symmetry that we have. Using our equation, I know that 25, since it's with my positive value, is my a value, not my b. Little typo there. That 25 is my a squared value. Ooh. Let's get that erased real quick. So 25 is our a squared value, which tells me that a is going to be at plus or minus 5. So that is going to be my vertices then, is at plus or minus 5, comma 0. Now my foci, I can't get right off the equation because 25 is my a squared and the 16 is actually the b squared value. And those would be giving me those like box points that we talked about to help us get our equations of our asymptotes. So I'm going to take the time to solve this right now, and by square rooting both sides, I get that b is at plus or minus 4. And on the graph, if we were to graph these box points, they would be y-intercepts since they're on the opposite axis as the vertices and the foci. Now to get the foci, this is where I have to use that equation that relates a, b, and c. Well, because this is a hyperbola, it's the equation c squared equals a squared plus b squared. Subbing in for my a squared and my b squared, I get 25 plus 16, so I end up getting 41 there. So c squared is equal to 41. From there, to find the foci, I'm going to square root both sides, and I get plus or minus the square root of 41 for this guy. Now the last thing left to do is to come up with the equations for our asymptotes that we end up with. So if I think about this, I'm going to go back to the graph first and kind of plot the things that we have on here and use those to help us. So I'm going to go to 5, comma 0, which is going to be right there. I'm going to plot my vertice and then do the same thing at negative 5, comma 0 and plot my vertice from there. The last thing left to do is to figure out what are these asymptotes on here, because I need to graph those so I can see the full shape that I end up with. Well, this is where those box points can help out. They're going to be at 0, comma 4, so I'm just going to put kind of a tiny little dot there, and at 0, negative 4. What this is creating is this kind of invisible box that goes through and creates a horizontal line at 4, a vertical line at 5, a horizontal line at negative 4, and another vertical line at negative 5. More importantly, it's going to give me my asymptotes. They're starting at 0, 0, and they're going up to my box point, then they're going all the way over to my vertice, which tells me that the equations for my asymptotes are going to be plus or minus 4, since I'm rising by 4, over 5, since I went up 4 and to the right 5. Now if I dash in my asymptotes there, I get that one going up. Over here I go down 4 and to the left 5, and I get that guy continuing on. I also get the negative 4 over 5. So down 4 and to the right 5, which is giving me this part of the asymptote, up 4 and to the left, and we're getting that guy right there. Now my hyperbola is based off of where my vertices are at. So they're going to start at my vertices, so I'll start at 5, 0, and they're going to curve open and get infinitely close to my asymptote on the top and do the same thing to my asymptote on the bottom side. Likewise, over on the right side, I'll start at this vertex and go up and over towards the top and down towards the bottom one, like that. This is everything that I would need to see on a graph of hyperbola. The asymptotes are necessary to draw since they do give us the shape of how kind of wide or how narrow each of these branches are, and then we also need to see the vertices labeled on there. Okay, let's look at our example B. I want you guys to go ahead and pause the video right now, and why don't you guys try example B. My hint to you is that it might not be in standard form to start with, so think about what you would have to do to get that into standard form. Okay, let's try example B. So my hint to you guys was that it's not in standard form to begin with. So if I start with this, I have 9y squared minus 4x squared equals 36. Now the reason I say it's not in standard form is if we go back to our notes on the prior page, both of these equations were equal to 1. And if I look at our example, for example B, I have an equation that's equal to 36. And so it's because of the 36 that I'm not in standard form. So to get this to be a 1, I'm going to divide through by 36, but whatever I do to the right side, I need to do to the left side. So when I simplify this down, I end up with y squared over 4 minus x squared over 9 equals 1. Now this guy is in standard form since I am equaling to 1 over here. The next thing I'm going to pay attention to is what type of hyperbola do I have? Well, my first term this time is y squared, but more importantly, it's the positive term versus the x squared is negative. So because y is positive here, I actually have a vertical hyperbola. What that means then is that my graph is going to open up and it's going to also open down. I also know that my a squared term is always coming from the positive, so in this case it's going to be 4. So a is going to be equal to plus or minus 2, but because it's attached to the y squared, it's going to be our y-intercept. So I'm at 0, plus or minus 2. Similar to before, the b squared term is always coming from the negative variable, so that's going to be the 9. So b is going to be plus or minus 3, and this is going to give us those box points again that I was talking about that help us get our asymptotes. Now since these are not on the same axis as the vertices, then since the vertices are y-intercepts, these are going to actually be x-intercepts that I get. From here, I can find my foci using that c squared equation. So we get c squared is equal to a squared plus b squared. Subbing stuff in, we get a squared was 4 plus b squared is 9. So we get that c squared is equal to 13. So that tells me that c is equal to plus or minus the square root of 13. My foci are on the same axis as my vertices, so they are also going to be y-intercepts. So we're at 0, plus or minus the square root of 13. I'm going to start by graphing this stuff that we have. So I have a vertex up here at 0, 2, then one down here at 0, negative 2. My box points are at 3, 0, and at negative 3, 0, and that's just going to help me get my asymptotes. So from the origin, I'm going up to my vertex, going over to my box points, and I'm getting this asymptote there. Likewise, I'm getting the rest of the line going down to the left. So that tells me that my equations of my asymptotes are going to be y equals, now I'm rising by 2, and running by 3, so plus or minus 2 over 3 times x. And the negative one will go down 2 to the right 3, and I'll get that line as well, and the rest of it going up over to the top left. The last thing I have to do is to actually graph my hyperbola. Now that I have the asymptotes, I have an idea of how wide it's going to open up. So I'm going to start at my vertex, which is up at 0, 2, and I'm going to curve this out. Let me make that curve a little bit better. We're going to get this guy to curve up and over, likewise over to the left side. And on the down portion of this is curving down and over, and the same thing over there. And there's our second example for given the equation, find all the important pieces of information and graph our hyperbola. Our next type of example here, we're going to look at what's the flip to this. What if they give us pieces of information and they ask us for the equation? So they're saying, what is the equation of the hyperbola in standard form, centered at the origin, with vertices at plus or minus 4, 0, and a focus at 5, 0. Well, the first thing I know right off the bat is that my vertices are my a values. So that tells me that my a is plus or minus 4, so my a squared is going to be equal to 16. I know that that's always going to be in my first term. What I need to know is what type it is. Well, my vertices and my focus here that are given are both x-intercepts. What that tells me then is I am looking at a horizontal hyperbola in this case. So I'm looking at the general equation where the x squared term is going to be positive. So x squared over a squared minus y squared minus y squared over b squared is equal to 1. So if I start to kind of play fill in the blanks here, I've got x squared over 16 minus y squared over, well, I need to figure out what b squared is. Now, my focus is not my b value. My focus is what c is equal to. So c is equal to 5 and also negative 5 since it is symmetric. So that tells me that c squared is equal to 25. Well, I can use that equation that relates a, b, and c to figure out what b is. So for a hyperbola, that will be c squared equals a squared plus b squared. So I get 25 is equal to 16 plus b squared. Now the last thing I gotta do is subtract 16 over to get b squared by itself. And we get that 9 is equal to my b squared, so b is plus or minus 3. Now I didn't need to go all the way to figure out what b is because all I needed to plug in was my b squared. So since b squared is 9, I can sub in and I get x squared minus 6 over 16 minus y squared over 9 is equal to 1. And that will be our final answer there for our equation of the hyperbola with vertices at plus or minus 4, 0, a focus at 5, 0, that is centered at the origin. Okay, why don't you guys try our third example? Okay, here's our last example dealing with just hyperbolas. So it says, what is the equation of the hyperbola in standard form, centered at the origin with a focus at 0, negative 8, or I'm sorry, a vertex at 0, negative 8, and a focus at 10, 0. Well, right off the bat, we know that our vertex is our a value, so that tells me that a squared is going to be equal to 64. The other thing I want to pay attention to is what type of coordinate pairs are these? And I'm realizing now that I actually have a typo on here. We're going to need to go ahead and change our focus to be at 0, 10, because it's not possible to have a vertex that's a y-intercept and a focus that is an x-intercept. So that's a little typo there for us to change. I'll change it on your guys' paper before I post it, but pretend like that it said 0, 10 the whole time. Since both of these are now y-intercepts, then that tells me right off the bat that I have a vertical hyperbola. What that means then is that my y squared term comes first, so I have y squared over a squared minus x squared over b squared is equal to 1. We have our a squared value, but what we're after again is our b squared. So our focus is our c, which tells me that c squared is going to be equal to 100. So I can use that relating equation, c squared equals a squared plus b squared. Substituting in, I end up getting 100 equals 64 plus b squared. Subtracting it over, and we get 36 is equal to our b squared, which is the missing link that I needed. So my final answer then is going to be y squared over 64 minus x squared over 100 equals, not over 100, over 36, since that's why we found our b squared. So x squared over 36 equals 1. And that is going to be our final answer for our equation of our hyperbola. I'm not sure if you guys have noticed on it, but if I look at both of these examples, the c value is always bigger than the a value. So here I had plus or minus 10 and then plus or minus 8. On example 2, we had 5 and 4. And if we go back to our graphs, I have numbers here where the vertices are smaller than the foci. Now the reason that happens, if we go all the way back up to the equation, is let's look at the graph. The foci is always inside my equation that I get here, so I have to make sure that the foci is a bigger value, so it's inside where the hyperbola is opening to. So it should be bigger than our vertices. So as a little reminder here, we can kind of add that and the fact that c is always going to be bigger than a. So down here we can add that c is always going to be bigger than a, and the reason being is so that our focus can be inside where our hyperbola is opening up to. Okay, let's look at our last set of examples. Now this is going to combine everything from this unit, and it's how to determine which type of conic section I have based off of just the equation. So up here at the top, I have the standard equation for a circle, the two parabola ones depending on if it was horizontal or vertical, the same thing for a horizontal and vertical ellipse up here, and also for a horizontal or vertical hyperbola that we're looking at. Now, I want you guys to pause the video right now and compare all four of these together. What are some differences that you see and what are some similarities, and try to list as many as you can. Okay, one of the first differences that I notice right off the bat is with a parabola. So a parabola is kind of a special case on its own, and the reason I say that is it only has one variable that is squared. So in both of these scenarios, I either have y equals x squared or x equals y squared. More importantly, I only have one of those variables squared, versus in a circle, an ellipse, and a hyperbola, both x and y are both squared. So an easy way to identify a parabola is the fact that only one of the two variables is going to be squared. Now if I'm in standard form, an easy way to identify an ellipse and a hyperbola is that they're both going to be equal to 1, versus a circle could be equal to 1. That could happen if r is equal to 1, but if r is anything bigger than 1, then I'm going to have it equaling another number. When it's not in standard form, that's when it gets a little trickier, and we want to divide through and try to make it look like an ellipse or hyperbola and see if that will work. The difference I notice between an ellipse and hyperbola is the plus sign on an ellipse and the minus sign on a hyperbola. Let's put this into action now. So we have 4 examples below, and it says for each of the following equations, determine if the equation is representing a circle, parabola, ellipse, or hyperbola. So let's take example 4. I have x equals 23 times y squared. Right now, what do you think that equation is representing? Well, based off of the fact that x is not squared, I'm pretty sure that this is going to be a parabola, since I only have one variable that is squared. If we look at example 5, I want you guys to take a moment and think about which of the 4 types you guys think example 5 will be. Now when I look at example 5, it kind of looks like a circle because I've got x squared plus a y squared equals a number that's not 1. But I also have these scalars, or these coefficients, in front of x squared and y squared. Now when I look at the equation for a circle, I have nothing in front of the parentheses on either one. So I actually need to get rid of these. They're both equal to 36, so I'm going to divide each term by 36. So I keep the equation balanced. When I do that, I end up with x squared plus y squared equals 1. Now, it's equal to 1 now, so that would make me think that it's an ellipse or hyperbola, but it's actually going to be a circle. And the reason being is that both of the x squared and the y squared are divided by the same number. They're increasing at kind of the same rate there. Versus in an ellipse or hyperbola, I would have two different denominators down here. Okay, one last time I want you guys to pause the video and decide on 6 and on 7. Okay, let's look at example 6. So it kind of looks like a circle again because I have no fractions. I have x squared and a y squared, so it can't be a parabola, but I still have to get rid of these coefficients. So I could divide through by 4 and it would cancel this guy out, but over here I'd still get left with a number. But if I divide through by 16, then I'm not getting rid of the fraction on the first term. So instead, I'm going to actually divide through by 64 since it's the largest value. And when I do that, then I get x squared over 16 plus y squared over 4 is going to be equal to 1. Well, this is the standard form for an ellipse. Since I have an x squared over one number plus a y squared over a different number, and so because those two are not equal, they can't be a circle. So since there's a plus sign and they're not equal, then it must be an ellipse. And for our last example, I'm going to do something similar. So I'm going to divide through by 225, since that is the largest number I have there. When I do that on each piece, we end up with x squared over 25 minus y squared over 9 equals 1. Well, the negative sign is a good giveaway that I do have a hyperbola here, and that would be true. Now, as kind of a follow-up, let's think about which type of an ellipse this is. Well, if I'm looking at an ellipse, I'm paying attention to which is the larger denominator. So because 16 is larger than 4 and 16 is with the x, this means that this is going to be a horizontal ellipse. On the flip side, when I'm looking at a hyperbola, I'm looking at which term is positive. So since it's x squared minus y squared, then this is going to also be a horizontal graph because the x squared is positive. So I have a horizontal hyperbola because the x is the term that's greater than 0 or positive. I have a horizontal ellipse up here because the 16 is bigger than the 4 and the 16 is with our x term. This can get a little confusing for people now that we have all 4 that we're trying to keep straight in our minds, so it's important to remember back to the basics on how do I determine for each shape which type of graph I have, horizontal or vertical. That is the end of learning target 10C for us, and it's also the end of this unit.